Now, let's take a look at the available load cases and the way to define them. The goal of building models is, of course, to have them provide results. These results will be reliable only if they are computed using reliable models and well-defined load cases. For that matter, proper computation schemes are required to make sure results will be accurate and produced as fast as possible. This is especially true when the computation is aimed at certification, since this process requires running a large number of load cases. So the software should be able to facilitate the definition and storage of load cases in a library, as well as run quick computations, potentially distributed among several computers. Most load cases used for the design and certification of turbines are related to wind. Wind can be constant, may include some turbulence, and can also be defined for gusts. All this for various wind speeds and orientations. As shown on the screen captures, input parameters in the dialog boxes are the standard ones widely used for wind definition or gusts, as in this illustration. 3D turbulent wind fields can be defined via external files. We have our own file format, which is fairly easy to reproduce, so connecting any wind generator to our solution is equally easy. In fact, interfaces for GH-bladed and Flex 5 wind files already exist. Wind without turbulence can also be input via point-by-point or analytical definitions. Once wind is defined, the user defines the event to be computed. Normal operations, startup, e-stop. In case it would be needed, it is also possible to create so-called advanced load cases where one can define independently the aerodynamic loads, the pitch behavior, and the brake, etc., to simulate, for example, the event where a pitch actuator would be jammed. Just like every other piece of data or model, load cases can be stored in libraries for later use. Because of the large number of load cases that are usually created or imported, it's easier for users to convert all of them into analyses ready to be run using a few default parameters, which can be immediately modified for any analysis. This short demo shows how easy it is to import a set of load cases and use this set to run computations for all of them. The user needs to go and get the corresponding file from the library. In this case, we will just use a subset of them and convert them into analyses ready to be launched. The definition of each of them can still be checked and modified if needed. Once everything is okay, a small click on the Launch button will start the chosen analyses. Using the library to store previously defined load cases also applies to certification load cases. The corresponding library is not yet provided by default. However, it will be added in later releases and will then be available on demand. Programs for automatic reporting also exist outside this tool and can easily be connected to generate the much-needed reports without having to rewrite everything each time. Based on these load cases, users can run two major types of analyses: transient or modal. Transient analyses correspond to the computation of the turbine's dynamic behavior. They're based on the Hilbert-Hughes-Taylor time integration scheme. Modal analyses, on the other hand, are performed on the entire turbine while operating. Since components closely interact with one another, most of the eigenmodes are coupled, and it's important to go further than just compute mode shapes for each of them independently. However, this can be easily done as well. Significant effects like centrifugal stiffening are naturally taken into account thanks to the fact that we use mass and stiffness matrices computed from the machine while operating, not at rest. Since certification and early design require running many load cases, we provide the opportunity to run computations not only on your local computer, but also on remote machines. Thanks to this, you can simply launch your jobs before leaving the office, and the results will be waiting for you the next morning.